Good afternoon, class. We are looking at exam 2 review, chapter 3, differentiation rules, covering from 3.1 to 3.8. Here's part 4, covering section 3.6, derivatives of the logarithmic functions. 3.6, derivatives of the logarithmic functions. Y equals ln x, we want to differentiate it. Since we don't know the answer yet, we are going to the exponential form of that, and we're going to write e to the power of y equals x. And so we're going to take the derivative of both sides implicitly, e to the power of y. The derivative is itself times y prime, and x is 1. So y prime is 1 over e to the power of y, and replace it with x. It's 1 over x, which means to take the derivative of y over ln x, just flip over the argument, 1 over x, and you're done. To expand that using the chain rule, this one is the same thing. Of course, we put an absolute value because of the restriction on the domain of law. Ln of g of x, 1 over g of x, times g prime ln of u is 1 over u du dx. In all cases, we want to pay attention to the fact that the argument of log must be non-negative. Reminding you of logarithmic properties. If b is larger than 0 and b is not equal to 1, y equals log x base b is equivalent to x being equal to b to the power of y. And as you look at this case here, you see they have the same exponent and they have the same base. In other words, if we look at this arrow, this is a general form, log x base b of y, it's b to the power of y equals x. If we can go from one format to the next, we have an easy time with that. So having said that, let's look at this general log and all the properties associated with that. Number one, I'm going to put a number so we can go back and forth. Log 1 base b is 0. That means log 1 with any base becomes 0. And log b base b equals 1. That means if the base and argument are the same is 1. This 2, log base b of b to the power of x is x, b to the power of log x base b is equal to x. 3 and 4 refer to the fact that logarithmic functions and exponential functions are inverse functions, and some of this we can just see with the arrow. For example, in this case, b to the power of 0 is 1, and so on. Number 5 is called the product rule. Log xy equals log x plus log y. They all have the same base, namely b. Log of x over y base b is log x base b minus log y base b. That's called the quotient rule. And finally, the power rule. Log base b of x to the power of n is n log base b of x. Now, we can go to common log. Log x base 10, we don't write the base, we just write log. That means the base is 10, and the equivalent format in an exponential form is 10 to the power of y equals x. Having said that, we should be able to see the transition from general case to a specific case, a common log. For example, of course, log 1 is 0, but this one is log 10, because number 2 says if the base and the argument are the same, the base missing means 10, therefore log 10. This is a natural log. A natural log, the base is e, so y equals ln x means log x base b. We don't write it in this format. And those are the properties. For example, ln 1 is 0, or in this case, ln e. Again, look at this one. The base and the argument must be the same. When we write ln, we know the base must be e, and therefore ln e must be 1. So that's pretty straightforward, everybody. When we look at the graph of exponential functions and logarithmic functions, because the two functions are inverse, they are symmetric with respect to the line y equals x. The change of base formula tells us log x base b can be log x over log b with any base, for example, a. More specifically, we go with the common log, log x over log b, or with a natural log, ln x over ln b, for the sake of calculation, because that's what the calculators can do. This point is the x-intercept located at 1, 0 for the log. And if x is between 0 and 1, log is negative. At 1, it's 0. And if x is larger than 1, then log becomes positive above the x-axis. And as I mentioned, the derivative of ln x is 1 over x. The derivative of ln x is 1 over x. The derivative of ln of g of x is 1 over g of x times g prime of x. This one is by the chain rule. Let's look at some example. Y equals ln of sine theta. So according to this formula, basically flip this over. Y prime is 1 over sine theta. And by the chain rule times g prime, so you need the derivative of sine, which is cosine theta. Cosine over sine is cotangent theta. Y equals e to the power of x over 1 minus e to the power of x. We have to use the quotient rule. We're going to call this f over g. And the answer is f prime g minus g prime f over g squared. So f prime, the derivative of e to the power of x is itself, times g, 1 minus e to the power of x, minus g prime, the derivative of the bottom, is, this is 0, minus e to the power of x, times f, the top is e to the power of x, and over g squared, just write whatever is at the bottom and put it in the parentheses and square it. As you notice, all we have to do is simplify the numerator. We'll do so. We get e to the power of x minus e to the power of 2x plus e to the power of 2x. E to the power of x times e to the power of x is e to the power of x plus x, or 2x. So e to the power r of 2x and minus e to the power of 2x, they cancel each other. The numerator is e to the power of x, and we are done. So y prime is e to the power of x over 1 minus e to the power of x quantity squared. Let's look at part C. Y equals ln x cubed, and we can do this two different ways. I'm going to look at both, and I want to emphasize this. This is simple enough that it really doesn't make much of a difference. In other words, if we just go with this 1 over g of x, that means y prime is 1 over x cubed times g prime, the derivative of x cubed is 3x squared, and it becomes 3 over x. However, the more complicated the log, the better the second method, meaning simplify this by putting the 3 in front. And so now you differentiate this. This is 3 times 1 over x, which is the same. And so this is a better methodology, everybody, if things get more complicated. All right, let's differentiate y equals log base 3 of square root of x. I want to remind everybody that we know how to differentiate when the base is e, but what if it's not? We can use the change of base formula. So we're going to write this as ln x over ln b. And it's important to know division by ln b means division by a number. That means 1 over ln b times ln x. This is just a number. Think of it as 2 or 5 or any number. So if you're differentiating this, you keep this and you differentiate ln x. Therefore, y prime is this times 1 over x, which means y prime is 1 over x ln b. And so to differentiate this, first we're going to change the square root of x to x to the power 1 half. Then we are going to use number 7, the power rule, and put the 1 half in front. And now we are going to differentiate. So to differentiate this expression, y prime is 1 half, you keep the number. X, flip it over 1 over x. You look at the base, is the base e? If so, you're done. If not, we need 1 over ln b, so 1 over ln 3. And you put them together as follows, 1 over 2x ln 3. That is the final answer. What about f of x equals log base 5 of x squared plus 1? Well, in essence, you have the same answer and you tag along the chain rule, which means the derivative of log f of x base b, you flip this over, 1 over f of x. You multiply by f prime of x by the chain rule. And as you look at the base, you notice it's not e, 1 over ln b. That's all. And you can put them together. So having said that, first we want to simplify. This can't be simplified further. So f prime is, flip this over, flip the argument over, 1 over x squared plus 1. And by the chain rule times the derivative of x squared plus 1, which is 2x. You look at the base is not e, 1 over ln 5. Put them together. As you can see, 2x is the only one that belongs to the numerator. And so you have 2x over x squared plus 1 times ln 5. Y equals ln of 5x over x squared plus 5. If you want to differentiate just the way it is, you have to flip this over and then differentiate it using the quotient rule. However, we are going to use logarithmic properties first. And the first thing we do, we use the quotient rule, ln of the top minus ln of the bottom. Then on this one, we can use the product rule, ln of 5 plus ln of x. Now it's completely decomposed, which means it's a lot easier now to finish the job one by one. ln 5 is a number, everybody. The answer is 0. We're going to differentiate. ln x is 1 over x. So this gives you 0, this gives you 1 over x. This piece minus, flip it over, 1 over x squared plus 5 times 2x. So believe it or not, this is the end of calculus. Now we are going to look at more algebraic steps. We take a common denominator of x times x squared plus 5. So this becomes 1 times x squared plus 5. And this becomes minus 2x times x. To simplify this, we are going to write x squared plus 5 minus 2x squared these two combine into minus x squared. Everything else remains. G of x is log of 9 minus x cubed to the power of 4. First, we are going to decompose the log using number 7, the power rule, by putting the 4 in front. Now we are going to differentiate. So g prime of x starts with number 4. Then you flip this over. I'm looking at this one, 1 over f of x. That means 1 over 9 minus x cubed. Then by the chain rule times f prime of x times the derivative of 9 minus x cubed, which is negative 3x squared. Finally, you look at the base. The base is missing. That means the base is 10, 1 over ln b, 1 over ln 10. And we are done. We put them all together and we end up with what's in the numerator? 4, 1, negative 3x squared. That means negative 12x squared. What's in the denominator? 9 minus x cubed times ln 10. And this is the final answer. Differentiate y equals 1/2 ln of 1 plus x over 1 minus x. And definitely we want to decompose the log completely. So to do so, before we start differentiating, we start working on logarithmic properties. This piece, we are going to go with number 6, the quotient rule, log of the top minus log of the bottom. So 1/2 remains, ln of 1 plus x minus ln of 1 minus x. So first we decompose the log. Then we're going to differentiate. To differentiate, we keep the 1/2 intact. And we're going to do each one. ln of 1 plus x. Following this is 1 over g of x. That means 1 over 1 plus x times g prime times the derivative of the parentheses happen to be 1. Write it just to be on the safe side. Minus 1 over 1 minus x times the derivative of the inside. Now, the derivative of the parentheses is no longer 1. This one is negative 1 times negative 1. So, in essence, you're looking at 1 over 1 plus x. And what is this one? Negative and negative, positive 1 over 1 minus x. So you want to add these two fractions, which means you have the 1/2 and you have the LCD 1 plus x times 1 minus x. So 1/2 the LCD. This one is 1 times 1 minus x. And this one is plus 1 times 1 plus x. So 1 times 1 minus x plus 1 times 1 plus x. So I'm showing you step by step what we have. And of course, we are going to simplify. You notice that you have 1 minus x. So let's write it here. And the numerator, minus x and x cancel each other. 1 and 1, they add up to 2. So you notice 1/2 and 2 cancel each other. So the numerator becomes 1, and you can write that in this format or 1 minus x squared. Either way is fine. Y equals ln of 5x. If it helps, literally write this ln of g of x. So 1 over g of x. That means y prime equals 1 over ln of 5x. Then g prime of x. Just take the derivative of ln 5x. What is the derivative of ln 5x? 1 over 5x times 5. Okay. So again, change it to g of x, h of x, f of x, whatever you want, and follow that. Now, clearly, this 5 cancels out this 5. The numerator is just 1, and the denominator is x times ln of 5x. And that's the final answer, everybody. We want to find an equation of a tangent for y equals x squared ln x at 1, 0. In order to do so, we need a pair which is given. We also need the slope, which means we have to differentiate first. To do so, we recognize this as the product of x squared and ln x. We put a raised dot. It's f times g. So we need f prime g plus g prime f. F prime is 2x times ln x plus ln x is 1 over x times x squared. F prime g plus g prime f. Let's write that top up. And so 2x ln x and 1 over x times x squared is just plus x. So that's y prime. What is the slope? Plug in number 1. It's important to know this is not the slope. When you plug in a value for x becomes the slope. 2 ln 1 plus 1, ln 1, everybody should know is 0. So we get 1. And we use y minus y1 equals m times x minus x of 1. Y minus 0 is 1 times x minus 1. And therefore, the answer is y equals x minus 1. That is the equation of a tangent line at 1, 0. Needless to say, the pair works for the original function. It should work for this one, and it does. Which means this, if when it does, it means this part is done right. Y equals log base 3 of 1 plus theta ln 3. We want to differentiate that. The very first step, can we simplify this? Can we decompose this log further? The answer is no. So there are a couple of ways to approach it. One way is just to do it the way it is. The moment you see log, you start with this 1 over f of x, in this case, 1 over f of theta in essence. So 1 over the argument. So y prime or dy d theta is 1 over 1 plus theta ln 3. Then we need f prime. Then we need the derivative of the inside. 1 gives you 0. Theta times ln 3. Please understand, ln 3 is a number. So ln 3 times theta, the derivative is ln 3. And finally, you look at the base. Is the base e? The answer is no. 1 over ln b, 1 over ln 3. And so, of course, these two cancel each other, right? So you end up with 1 over 1 plus theta ln 3 as the final answer. Also, class, you may recall what we mentioned about the change of base formula. This equation is the same as writing natural log of the argument 1 plus theta ln 3 over ln 3. This is the change of base formula. Y equals ln 2 e to the power minus t sine t, and definitely you don't want to differentiate it the way it is. Rather, you want to use your logarithmic properties to simplify first and foremost, which means we are going to look at each piece first, and we're going to start with the first piece, ln of 2. We are looking at the product rule. So ln 2 plus ln of e to the power minus t plus ln of sine t. Now, what is this one? Ln of e to the power of x is x, so this is equal to negative t. Now, we are ready to differentiate. To differentiate, we're going to do it piece by piece. Y prime equals, we start with ln 2. ln 2 is a number. The derivative of ln 2 is 0. Minus t, the answer is minus 1. ln of sine t, 1 over sine t times its derivative, cosine t, and we are following this. And so what you're looking at, it's minus 1 plus cosine over sine, which is cotangent t. That's the final answer, everybody. What about y equals t log base 3 of e to the power of sine t ln 3? Again, use your algebraic techniques and properties of logs to simplify as much as you can. You may notice we have the base here, e, and ln 3, and I hope everybody remembers that ln of e to the power of x is x, or e to the power of ln x is x, and log base b of b to the power of x is x. Therefore, reminding you of that, we're going to put these two next to each other in the following manner. So t remains, log base 3 remains. This part is the same as this one. You just say, instead of sine t times ln 3, commutative property of multiplication, ln 3 times sine t. What is e to the power of ln x? X. What is e to the power of ln 3? 3. So this can be replaced by 3. Now take a look at this one. Log base 3 of 3 to the power of sine t is simply x. That means it's really sine t. Or you can bring the sign in front. You can bring the sign in front and say t remains times sine t times log 3 base 3, and this is 1. If it makes it easier, you can do it that way. Okay, this is 1. And so you have t times sine t, which means we're going to use the product rule of differentiation. So I hope you see knowledge of algebra, properties of logs can make life easy. So for calculus, f prime g plus g prime f. So y prime would be 1 times sine t plus the derivative of sine t is cosine t times t. So the final answer is sine t plus t cosine t. Logarithmic differentiation, y equals x to the power of 3/4 square root of x squared plus 1 over 3x plus 2 to the power of 5. What is logarithmic differentiation? Generally speaking, it has some usage. For example, when the function is very complicated. That's one use of that. So what is the process? Number one, take the natural log of both sides and of course, decompose and simplify. So if I take the natural log of the left side, I get ln y. If I take the natural log of the right side, what do I get? Ln of the top minus ln of the bottom. Ln of the top is ln of x to the power of 3/4 plus ln of square root of x squared plus 1 minus ln of 3x plus 2. Let me just write it down here and then. So we have ln y is ln of x to the power of 3/4 plus ln of x squared plus 1 square root. I'm going to write it as x squared plus 1 to the power of 1/2 minus ln of 3x plus 2 to the power of 5. So that's what we get, everybody. So let's do one by one. 3/4 sits in front. So we get 3/4 of ln x. 1/2 comes in front. Half of ln x squared plus 1. 5 sits in front. Minus 5 ln of 3x plus 2. And so this is purely algebra and using properties of logs to decompose. And the next step is to differentiate implicitly. So we start with the left side, ln y becomes 1 over y times y prime or dy dx. Let's start with this one. 3/4 remains. Ln x becomes 1 over x. This one plus 1/2. So in other words, the coefficient remains. Flip this over, 1 over x squared plus 1. And by the chain rule times its derivative, which is 2x. This one minus 5 remains. Flip this over, 1 over 3x plus 2. And by the chain rule times its derivative, 3. And believe it or not, this is it. This is the end of calculus. Everything else is using algebraic techniques. So what do we do now? Of course, we are going to solve for dy dx. So how do you solve for dy dx? You multiply both sides by y. In other words, take 1 over y to the other side. So parentheses, y. So to do that, you're going to say dy dx is y times the parentheses. This is 3 over 4x. This one is x over x squared plus 1 minus 15, 3x plus 2. So you get dy dx is y times 3 over 4x plus x over x squared plus 1 minus 15 over 3x plus 2. The final step is to replace the y with this expression. And you're done. Logarithmic differentiation continues, y equals x to the power of sine x. So one other usage of logarithmic differentiation is when what you have is an expression where the base as well as the exponent are both functions of x. We've dealt with the case when one of them is a function, one of them is a number, is either the base or the exponent. This one, both of them are. So one way is logarithmic differentiation, and you start with taking natural log of both sides. And so if you take the natural log, the sine x sits in front. And now we are going to differentiate implicitly with respect to the independent variable. It happened to be x. So obviously the left side, ln y is 1 over y times y prime. And the right side uses the product rule for differentiation. So f is sine, so f prime is cosine times g, which is ln x, plus g prime, ln x gives you 1 over x, times f, which is sine x. And so what is y prime is the right side times y. The right side is cosine x ln x, 1 over x sine x. So we want to solve for dy dx or y prime. And the final answer to replace the y with x to the power of sine x. And we're done. Now, this is one way to do it. The other one is to use the exponential method as follows. Everybody knows e to the power of ln x is x. So if that is the case, we are going to replace this x with e to the power of ln x. So it's e to the power of ln x to the power of sine x. And what does that mean? That means e to the power of ln x times sine x. And this, I leave it for you to differentiate. We know how to differentiate exponentials, and you end up with the same answer. So when the base and the exponent are both functions of the independent variable, in this case is x, then you either use logarithmic differentiation or the fact that e to the power of ln x equals x to differentiate. Derivatives of inverse trigonometric functions. The derivative of sine inverse is 1 over square root of 1 minus x squared. Tan inverse is 1 over 1 plus x squared. Secant inverse is 1 over x squared of x squared minus 1. What about the rest of them? Cosine inverse, cotangent inverse, and cosecant inverse. Identical, each and every one of them will become negative. So the derivative of cosine inverse is the same as this one, but negative 1 over square root of 1 minus x squared. The derivative, the dx of cotangent inverse is negative 1 over 1 plus x squared, and cosecant inverse is negative 1 over x squared of x squared minus 1. And I want to remind you how we actually arrive at that, and we're going to look at a couple of examples and the proofs, because sinusoidal functions, or for that matter, trigonometric functions, none of them is one-to-one. We had to restrict the domain, for example, for sine from minus pi over 2 to pi over 2 to make it one-to-one. And now it gives rise to sine inverse. So when we say sine inverse of x equals y, that means sine of y equals x, and y is between negative pi over 2 and pi over 2. Remember, this was the domain for sine x, the restriction, and now it's the range for its inverse. Therefore, sine inverse of sine x and sine of sine inverse of x, both of them become x. It's important to understand this x belongs to sine x. The restriction is x is between negative and positive pi over 2, but this x belongs to sine inverse, and therefore x is between negative 1 and 1. And the same thing for cosine. Cosine inverse of cosine is x. Cosine of cosine inverse of x is x. Understand, in the case of a cosine, the restriction was between 0 and pi. That originally was on the x. And now this is all the um, derivatives of inverse trigonometric functions. So we'll look at the proof for a couple of them. For example, let's go with sine inverse. And again, sine inverse of x equals y means that. So to prove that, we're going to start with let sine inverse of x be some function such as y. We want to find the derivative. We know the derivative of sine inverse is 1 over 1 minus x squared. So we want to get there. All right. So to do so, we are going to rewrite this. The meaning of sine inverse of x equals y is that sine y equals x by the definition of inverse functions. And now we are ready to differentiate both sides implicitly, which means sine, the derivative is cosine. So we get cosine y, and y is a function of x dy dx, and x is 1. So cosine y dy dx is 1. So what is dy dx? 1 over cosine y. If sine y is x, cosine y is what? Remember, sine squared plus cosine squared equals 1. So cosine squared is 1 minus sine squared. Cosine y is plus minus square root of 1 minus sine squared. The restriction is that this belongs to the fourth and first quadrant where cosine is positive. That's why we use only positive. So cosine y squared of 1 minus sine squared y, which is 1 minus x squared. So 1 over the square root of 1 minus x squared is the answer, everybody. So we proved that the derivative of sine inverse x is 1 over square root of 1 minus x squared. Let's work on tangent as well as another example. A tan inverse of x equals y, tan y equals x. The restriction on tangent was similar to sine between negative power 2 and power 2. The endpoints are not included. So by definition, if tan inverse of x equals y, that means tan y equals x. And we want to prove that the derivative d dx of tan inverse of x equals 1 over 1 plus x squared. So again, we are going to do the same thing. We are going to differentiate both sides here implicitly. Tan, the derivative is secant squared. So secant squared y, dy dx, x gives you 1. One more time, tan, secant squared, same argument y, and then y is a function of x, dy dx by the chain rule. The right side is 1, therefore dy dx is 1 over secant squared y. Another Pythagorean identities, we had 3 Pythagorean identities in trigonometry. One of them was sine squared plus cosine squared equals 1. And one of them is 1 plus tan squared is secant squared. And one of them 1 plus cotangent squared is cosecant squared. So we use this. And secant squared y is 1 plus tan squared y. So what is tan of y? X. So 1 plus tan squared, that means 1 plus x squared. And so you replace it. Dy dx is 1 over 1 plus x squared. So the derivative of tan inverse is 1 over 1 plus x squared. Let's differentiate y equals e to the power of 10x, tan inverse of x, and we notice is the product. So we're going to put the raised dot in between and use the product rule on that, which means we are going to differentiate the first piece. E to the power of 10x. Exponential is always itself. And 10x times 10 by the chain rule and times 10 tan inverse of x. This is f prime g. So let's just write f g. So this is f prime g plus g prime. Now the derivative of tan inverse is 1 over 1 plus x squared times f, which is e to the power of 10x. In other words, we have the following. F prime g plus g prime f. That's all. And now we are going to rewrite this. This 10 sits in front, 10 e to the power of 10x tan inverse of x. This one is the numerator plus e to the power of 10x over 1 plus x squared. What about y equals cosecant inverse of e to the power of x? So cosecant inverse would be negative 1 over x squared of x squared minus 1. It's important to understand this is not x, it's a function of x. So when that happens, you have two choices. You can say d dx of cosecant inverse of u is minus du dx, u squared of u squared minus 1. Or you can say this is g of x, so minus 1 over g of x squared of g of x quantity squared minus 1 times g prime. So let's go with that. Again, bear in mind, g of x is e to the power of x. Let's in fact write it so everybody can see we are using this as g of x. So dy dx is negative 1 over something here, squared of something squared minus 1. This is g of x or e to the power of x. So is this one. And then you need g prime. The derivative of e to the power of x happen to be also e to the power of x. So right here, you put e to the power of x, whatever the function is. And the g prime here, you put e to the power of x. So what happens is this cancels out this one. Dy dx becomes minus 1 over the square root of e to the power of x quantity squared. That means e to the power of 2x minus 1. Y equals x sine inverse of 3x. Again, we notice this is the product of x and sine inverse. We put a raised dot in between. F times g, so we're going to use f prime g plus g prime f. So starting with x, we get 1 times g, which is sine inverse of 3x. Plus, now sine inverse of 3x, again, remember, sine inverse is 1 over square root of 1 minus x squared. So if it's sine inverse of u is du dx squared of 1 minus u squared. If you go with this format, write it as d dx of sine inverse of g of x, which means think of this one as the g function now. Okay, so you put 1 over the square root of 1 minus g of x quantity squared times g prime. Therefore, we are going to put it in this format. What goes in here? G of x. What goes in here for the top is g prime. So we put 3x here, 3 here. And so this is simply sine inverse 3x. This is 3 over square root of 1 minus 9x squared. And times f, I forgot to mention that, times x, because f prime g plus g prime f. And so this is sine inverse of 3x. This is plus 3x over 1 minus 9x squared. Y equals x cosine inverse of x minus the square root of 1 minus x squared. To differentiate this first and foremost, this is the product of x and cosine inverse. We put a raised dot here. Secondly, we change this to 1 minus x squared to the power of 1 half to make it ready for the power rule, or better yet, the extended power rule in essence. So having said that, let's work on this as writing it as f g. So we have f prime, which is 1. So dy dx is 1 times cosine inverse plus. Now cosine inverse is negative 1 over the square root of 1 minus x squared times f or x. And we're done with this. Now we are going to move here, and this is something we've seen a lot using the extended power rule, minus 1 half 1 minus x squared to the power of 1 half minus 1, which makes it negative 1 half, times the derivative of the inside, which is negative 2x. And this is the only calculus step we are going to simplify. So first, this is very easy. This is simply cosine inverse. This is minus x over the square root of 1 minus x squared. Let's see what happens to the brackets. I want to make sure we understand how we simplify the brackets. First and foremost, let's look at this one. You put 1 and negative 2x at top, you have negative 2x. You put 2 at the bottom, and this one, negative 1 half, goes down, becomes positive 1 half. So again, 1 and negative 2x, the product is negative 2x. 2 remains at the bottom. 1 minus x squared goes down, the power of 1 half. And so two things that I want you to pay attention to. Number one, we are going to drop the 2, and this becomes minus x. Number two, this negative makes this positive. And don't forget, this is negative. So again, this is cosine inverse. This is minus x over square root of 1 minus x squared. This is plus x over the square root of 1 minus x squared. And these two cancel each other. The final answer is dy dx equals cosine inverse of x.